Okay, in this video we have integral of cosine x e to the sine x dx. And we're really grateful that we have that cosine sitting alongside the e, because otherwise we'd really be in a lot of trouble here. But fortunately we have e to something, so let u be that something. And then we would differentiate to say, well, what do we need to have for du to carry the du through? And turns out derivative of sine is cosine x dx. So we have exactly what we need to carry the substitution through. So here I am going to write this out just a little bit more so that it's clear how everything kind of fits together. If we didn't have that cosine out there, then we'd be dealing with integral e to the sine x, and we'd kind of be, I really don't know where to go with this. I really don't have an idea of where to go. What could I do? How could I make it work out? We'd really be at a loss right now. But since we do have the cosine, it's exactly what we need to carry the substitution through. So we can go ahead and work that out and say, well, that would be e to the u du. Integral of e to the u is just e to itself. So that's actually just going to become e to the sine x. And don't forget, plus a constant. So integral of cosine x e to the sine x is actually just going to be e to the sine x. And if you reverse that process and do the derivative of this, then by the chain rule you'd get back cosine x e to the sine x. And so now we've worked that one out. Let's consider one more here. Here we have integral of e to the square root of x dx over square root of x. And things are looking kind of bad here with those square roots hanging around. So still we have e to the something, so really not much more we can do except, hey, let u be that something. And for the sake of convenience, I'm going to rewrite that as x to the 1/2 instead of square root, because it's easier for us to talk about its derivative. So when we differentiate, du would be the derivative of x to the 1/2, which would be 1/2 x to the minus 1/2. And of course, don't forget about the dx. So as we occupy here e to the u, right there we have it right there. We've accounted for that. So the rest of the stuff is 1 over square root of x. Well, 1 over square root of x can also be thought of as x to the minus 1/2. So we have the variable part of what we need to carry the substitution through. The 1/2 that we're missing, that's no big deal. That's just a number. So the stuff that's left over after we've occupied the e to the u is exactly what we need to have left over, at least in terms of the variable. Constant 1/2 isn't there, but we can fix that easily enough. So we can go ahead and say, hey, that's going to be e to the square root of x times, we need a 1/2 x to the minus 1/2 to go with our dx. Now we already had the x to the minus 1/2. That's what the 1 over square root of x did. But we didn't have the 1/2. So I put a 1/2 here on the inside that was not part of the problem. So I have to account for that by putting a 1/2 on the outside, or dividing by 1/2 on the outside. So I multiply by 1/2 on the inside, so I divide by 1/2 on the outside, or alternatively, multiply by 2. Now everything's set up. I have e to the u and du. So now we just carry the integration through. 2e to the square root of x plus a constant. And now we've done the derivative here. And this is pretty standard for derivatives involving e to the x. Pretty standard approach to handling these problems. And hopefully this will get you started, help you to understand the other examples that you'll find in the course notes. And as always, if you have questions, please ask.